meet in an hour.
I think 2 hours.
2 hours, sure, yeah, that's better.
How'd you come sit down here?
Can you leave some of the front seats available for the chair and the committee members?
Wally.
And Wally.
And Linda and Dave, said your parents.
What's that?
What are your parents' names?
Oh, Linda and Jim.
Jim, are they coming?
Unfortunately not. I made a pretty big error and told them to come for graduation instead of the defense, which in retrospect is the wrong thing.
Oh, yeah.
But
Which algorithm is playing?
someone in the room is playing. I don't know exactly who.
Pretty evocative.
Don't be shy.
Terrible outside. I parked on the top of Gilman.
You parked on the top of Gilman? You're still parking?
Right.
There was parking in Gilman?
Yeah, there was like one spot.
Sorry, Jen. Did you check it?
I did.
Oh.
I bought the bagels and then there and then
Sorry.
there was a bunch of visiting box. I know, but I reviewed for the private permit.
Picked a lousy day to defend.
Why?
Europe's is due at 1 today.
Right,
I
yeah.
have like 3 papers I haven't looked at.
Oh, jeez. I didn't think about that because I wasn't submitting this year. My bad. Who all is submitting? Anyone that I know?
I don't know, do you know Yao?
Yeah. She's up in Montreal now? Or Toronto, rather?
Toronto.
Yeah, yeah.
So you're gonna wake up
Toronto
on
would definitely.
I think so.
That's pretty awesome, yeah.
That is pretty awesome.
Yeah.
She's been there like 4 or 5 weeks and she hasn't been.
Wow. Wait, it's a work that she started after going? That's insane. That's
Yeah,
ridiculous.
she's working like crazy.
I'm gonna be a song.
That's the difference between working with Jeff and
might be
working
able to
with
do
me.
it, but I wouldn't know.
I see weeks versus months, or
Huh?
weeks versus months, or weeks versus days.
Weeks versus years.
Oh, I see. Maggie was telling me you presented a paper or a poster at BSS, a first author poster.
Yeah, who said that?
My girlfriend Maggie.
Hello.
Oh, hi.
She's in John's.
Were you at BSS?
Yeah, I think I came by your poster.
Oh, okay. I didn't realize.
It's
You
okay.
should have said something.
Hey Miller,
Why don't you do it tonight?
you can come up here if you want.
Which
There's.
lab are you from?
John Services.
Hey Nicole.
But I don't have a key to the new place yet.
Feel free to grab some
Housing is
food
the
if you want.
new place. And but my
Probably will wait 5 minutes or so.
like that.
Yeah, I need to wait for the committee to show up. Yeah, definitely. I don't know where Julian is.
I think they did it again.
Hey. Hey, you made it. One more committee member remains.
Everyone's giving me a lot of room, Chris.
What's that?
Everyone's giving me a lot of room.
Yeah, that's true. Maybe I smell or something. I don't know. I also have like an intimidating amount of stuff set up here, so I understand why no one wants to sit here. Oh, there's Shlomo. Yes, everyone showed up.
That's the real gist of this test.
Yeah. Sounds a lot more interesting when more than one person is using it.
Oh, you're supposed to use it.
Yeah, it's like if you go to this URL, you can play with it.
I haven't looked up there yet.
It's probably. Hey, Julian.
How's it going?
Pretty good. How are you? Long time no see.
Yeah, it feels like I've forever.
Yeah.
Safe answer, I like it.
Say, say.
I heard Anya dropped her phone in the toilet.
Yeah.
That happened.
Yeah.
Hey.
And then I was like, I'll put it in rice. And then she got rice on the charger, so it was bad, and she couldn't charge it.
The rice, how much that was maybe about 75 or?
Mine got the rice out, and her phone was working next time it was up. Sanitized.
It's not a great interface, I'm afraid.
Just threw a note to Joy, we'll see. Lots of typos.
Thanks.
Good, how are you?
I saw your food trucks the other day and I nodded at you and you didn't.
That's what it thinks about my entry.
What's that?
That's what it thinks about my entry.
Oh, did it try to play Ode to Joy?
No, I'm not going to stop.
Oh, I see.
It was, yeah, you can't deny it.
I think Chris might have told me this lie from his perspective.
What?
You can't blame me, I probably had tunnel vision for whatever
Oh, yeah,
I was waiting in line for.
I was recognized by it the other day. But I got on the cruise, I know that.
You gotta wear like a name tag.
I love it that they're starting to have documentary members who ride skateboards.
About time. Days of legal weed.
Five committee members. It's a miracle. Actual miracle. They're more briefcase. We might need to maybe. Actually, I'm not sure. Actually, I think it's probably fine. Ooh, someone actually played this.
So I'm interpreting this as a major scale, right?
What's that?
I'm interpreting this as a major scale. Is that
Oh, geez, it wrapped in the No, it's so it's the like the 8 buttons of my piano genie thing. So it's like doing the stochastic, miniaturized piano thing.
You get accepted?
I guess we can start whenever you like to.
Get accepted.
Oh, no, they haven't even used these yet. Some of these. This is, Yao after 5 weeks and Jeff,
And it's really my pleasure to be able to talk to you about my PhD research on enabling new musical interactions with machine learning. So I want to give a brief overview of my background, both as a musician and a researcher. So my musical journey started at the age of 3 when I started taking piano lessons, and I continued studying classical piano until the end of high school. And also in middle school, and throughout high school, I started studying percussion performance and played on drumline in high school, where I actually met a lot of the friends that are in this room today. So I consider both my piano and my percussion experience really to have kind of shaped me as a musician and also continue to influence the types of research projects that I'm interested in today. But in addition to music, for as long as I can remember, I've also been interested in computers and technology, and how music and computers can actually improve our skills as musicians and allow us to do things that we wouldn't otherwise be able to do. So for my undergraduate education, I actually decided to go to UT to study computer science, and towards the end of my degree there, I encountered a group of composers and technologists in the music department who were using computers to do what I thought were really impressive things. So I kind of immediately fell in love with the idea of programming a computer to make a sound, and knew that I wanted to go to grad school to study this. So that's kind of how I got to be here today. So I think back a lot on this experience, and I feel very fortunate that I was able to learn an instrument when I was very young, because over the course of my life, being able to create music on instruments and also using computers and audio software has brought me a lot of joy. But I think it's really unfortunate that the only people that get to experience that satisfaction are just the people who happen to be lucky enough to have learned an instrument when they were very young. Which brings me to kind of the mission statement of my recent research, which is to lower the barrier to entry for meaningful creative musical experiences for non-musicians. And what I mean by that is basically to build systems that allow people who would previously only have been able to listen to music to actually create it. And by meaningful, what I mean is I want it to be an experience that is not just them pressing a button and generating a song in a vacuum, but actually using tools with intention to build something to create something that they actually want to create and feel like they were involved in. So what exactly are the obstacles? Why can't we do this now? So I think as an illustration, let's look at a task that is currently only accessible to experienced musicians, which is the task of piano improvisation. And let's kind of break down the steps involved in this task and see what an expert musician actually needs to do to accomplish this. So arguably the first step is this idea of conceiving of a piece of music from scratch in one's head using what I like to call one's musical intuition. And then this musical intuition needs to be translated into a precise language, a musical language consisting of notes and rhythms. And then the performer also needs to plan out a series of actions that he or she will take to be able to play that sequence on the piano. And finally, the performer actually needs to have the motor skills to be able to input those actions into the piano in real time. Now I'm going to argue as we kind of go from top to bottom here, we're kind of actually stepping down some sort of like from higher level to lower level tasks in a cognitive sense. Now this is kind of debatable, but I'd argue that kind of the highest level aspect of piano improvisation is this idea of conceiving of a piece of music from scratch in one's head. Whereas, unfortunately, a lot of the training and experience and the years and years of practice that an expert pianist needs to do in order to be able to accomplish this task is actually more closely associated with some of the lower level skills, like learning to play scales very quickly and being able to input these patterns very quickly. So could we actually build systems which would kind of short circuit this process and allow us to more directly, or even possibly completely directly, translate our musical intuition into something that we can listen to? And I think this could potentially have a two-pronged effect for non-musicians, it would lower the barrier to entry and allow them to express musical intuition, which I believe many non-musicians have, more directly as sound that they could listen to. But for musicians, it might also allow them to it might kind of unburden them and free up the cognitive capacity that is currently associated with these lower level tasks, allowing a musician to focus mostly on the high level idea of having a piece of music in their head. So this arrow that I've drawn here is one of a category of things I like to call new musical interactions. And by that, what I mean is basically systems which allow us to manipulate, create, or otherwise experience music in a way that is not just passively listening to it. And so the arrow that I've currently drawn here from brain to piano is still very much science fiction. That's kind of what I would like to work towards, but definitely not something we can do today. But something that is slightly like a step below that would be something like this, a system which would allow a person to play on an air guitar, such as Beavis, who doesn't know how to play the guitar, and actually translate the gestures that Beavis is playing on the air guitar to corresponding musical gestures that St. Vincent might play on her actual guitar, thereby allowing someone who doesn't know how to play this instrument to actually have the overall experience of playing it. And so it's important to point out here that I'm kind of defining this idea of gestures. So in this case, the gesture is like being in front of a webcam and pretending to play the guitar. But they could also be many different types of things, which I'll talk about throughout the course of this talk. So far I've kind of unpacked the first half of the title of my thesis, Enabling New Musical Interactions with Machine Learning, but I've yet to really justify why we need machine learning to be able to do this. So the short story, my short answer to that is that machine learning essentially helps us make musical predictions on behalf of users. So what I mean by that is we can use machine learning to study a data set of expert composed music to extract patterns from it and ultimately come up with some system that allows us to answer questions about music in some sort of intelligent way. So one example system might be some sort of interactive system where the goal is to compose a melody alongside an algorithm. So the system is kind of assisting, for example, a non-musician in composing a melody, and maybe in the course of the melody, at some point, the note middle C is composed. And then the non-musician that is using the system might have an idea in their head of the next note they want to hear, and they might kind of roughly know that it is higher in pitch than the previous note based on their intuition, but they don't know enough about music to know exactly what pitch it is. So what we could do is we could feed this question to a machine learning system which has been trained on human composed melodies, and then output a series of predictions associated with confidences. So for example, the system might say with 50% chance an expert composer would have chosen the note D next. And kind of we can pick that note and move on. So interactive machine learning essentially allows us to go from this concept of a piece of music that's in our head to a series of gestures specified through some interactive system. And then machine learning allows us to translate those gestures into music that we can actually listen to. So this is kind of an overview of a couple of the projects that I'm going to describe today. But more broadly, my research sits at the intersection of music technology and machine learning. And specifically, I focus on the sub-areas of acoustic modeling, which is the idea of getting neural networks to actually operate on audio data, which is very challenging, at least out of the box. And also on gestures and interfaces, so designing interactive and user interfaces that people can actually use to benefit from these systems. And finally on music generation. And so all of the research that I've done, so all of the projects that I'm going to describe today kind of fall somewhere along this spectrum. And in addition, all of the research that I've done as a PhD student here at UCSD can kind of broadly be taxonomized into these categories. Cool. So that's kind of an overview. And now for the remainder of the talk, it's going to be in two parts. In the first part, I'm going to talk about applying machine learning to music and building machine learning models that do something interesting on music. And in the second part, I'm going to talk about building interactive systems which allow us to benefit from what the model has learned. So music can arise from very diverse sources, such as it can come from an orchestra, or from an electronic music show, or from a gamelan ensemble, et cetera, et cetera. But my claim here is that different pieces of music can be thought of as samples from some hypothetical probability distribution of music, which encompasses all of the music that has ever been written or could ever be written. So this is a structure that we don't know, but what I mean by this is like if we listen to a piece of music at random on our computer, we're essentially kind of implicitly sampling from a very biased version of this distribution, such as only the music that we like and that we have stored on our computer. So this is more than me attempting to make any sort of philosophical justification. I'm kind of presenting this as a conceit. This is just something that we're going to do in order to motivate the remainder of my research. But the point is that if we can actually characterize a distribution in this way, like if we could come up with some sort of computational representation of this distribution, we could actually compose new music simply by sampling from it, which would be very convenient. So of course the distribution of music is actually a joint distribution over kind of innumerably many random factors, like all of the things you can think of that can vary that would change a piece of music. Some examples are things like the genre or the style of the piece, or the composer of a particular piece, but also things we're less likely to know, like the type of microphone that was used during recording, or how much coffee the drummer had before that day of recording. So like basically some of these things we know and some of these things we can't really ever hope to know. So what we do in practice to make modeling this a little bit more tractable is that we kind of fix some of these attributes and investigate the others. So by training a machine learning system only on Bach chorales, essentially what we're doing implicitly is modeling the probability distribution of music given that the style is chorales and the composer is Bach. So this is one of a number of simplifying assumptions we're going to be making in order to actually try to model some portion of this thing. And the other thing we need primarily is some sort of representation, some sort of way of actually storing music in a computer such that we can compute things about it. And we have a number available, such as sheet music, which is familiar to musicians, or piano roll, which is kind of a time pitch decomposition of the sheet music, and also MIDI, which is a list of basically a list of all the points in time at which a piano roll changes and how it changes. And on the acoustic side, for actually waveforms, we have waveforms and spectrograms. So these are basically these contain all the information that the symbolic score contains and a lot more about a particular performance. But so as point of example, let's look at a very simple representation of music and a very simple way of calculating this as kind of an illustrative device. So our representation that we're going to choose is we're going to take a given melody and remove all of the rhythm and the octave information and simply represent it as a string of pitch classes, of equal tempered pitch classes. It's important to point out we've already thrown away a lot of information and also kind of restricted ourselves to only looking at music which can be well represented by equal tempered pitches. And so in order to actually calculate a number associated with this particular melody, so the likelihood of this particular melody, we have to pick what is called a factorization, which is some way of actually breaking down the problem so that we can calculate it. And in this case, the simplest thing that I can think of is representing the likelihood of a given melody as the product of the likelihoods of its individual notes. And to get the likelihood of specific notes, we can just simply count, we can take some piece of music that we might be interested in analyzing and count the number of occurrences of certain pitches divided by the number of the notes in the data set, which will give us a probability for each pitch class. Now this is a very simple representation, but I think it's also interesting that even such a simple approach can already highlight important stylistic distinctions between composers. So for example, here is two very different pieces of piano music, a C major prelude by Bach and a 12-tone piece by Arnold Schoenberg. And the result kind of obeys our intuition. So the likelihood of all of the 7 notes of the diatonic C major scale are much more likely from the C major Bach prelude, whereas all of the notes are kind of more flat and equally likely in the Schoenberg distribution, which is reflective of his compositional technique. And so we could also generate music from these distributions simply by sampling one note at a time from these likelihoods. So for example, if we were sampling from our Bach model, 20% of the time we would pick the note G and 2% we would pick the note F sharp. But this would obviously be a very bad way of generating music because it wouldn't have any sequential context. But what we can do with this model is ask the question, how likely is some other melody that we care about, such as Twinkle Twinkle Little Star? Not that anyone really cares about that. But so this allows us to answer this question. So essentially what I mean by this question is if we were to compose music by the simple algorithm I just described of picking one note at a time, what % of the time would we actually arrive at this particular melody? And from the Bach distribution, we only arrive there 2.8 times 10 to the negative 4th times, and a similarly small number from the Schoenberg distribution. But it's important to point out that it's actually 2 orders of magnitude more likely to happen from the C major Bach prelude distribution than the Schoenberg one. And all this is meant to illustrate is how we actually go about comparing these models between each other. Like, if we have 2 different probabilistic models of music and some other piece of music that we care about, how can we determine which model is a better fit? And this is essentially how we do it. But so I just mentioned that this is a really bad way of generating music because it won't have any sequential context. So how can we actually improve that? So the simplest thing we could do is to add the bare minimum amount of sequential context, which is often referred to as a Markov chain. So essentially what that means is that we could alter our predictions for a given pitch class, given the immediately previous pitch class. But of course, this would still not produce amazing music because it would only have kind of the bare minimum amount of context. What we really want is kind of a more generalized notion of this, which is often referred to as a language model, where essentially we should be able to alter our predictions for a given pitch based on all of the previous pitches that came before that pitch. And this would actually allow us to compose music that has more global context. But unfortunately, we can no longer just count the information in the data to get at this particular model. We actually now have to adopt a learning approach rather than a statistical approach. So one thing that I do in my research, or the tool that I use most often in my research to do this is called a neural network language model. And I'll give a very high bird's eye overview of how this essentially works. So at some point in some real sequence of music, we have the pitch class C. And what we do is we multiply that at the start of training by a randomly initialized matrix. So we have some vector representation of this pitch C, and we multiply it by a matrix, which gives us another vector. And that vector are commonly called hidden features. We don't really know what these numbers mean at this point, or maybe ever, but it's just important that we've gone from a discrete representation of pitch to a continuous one. And then we multiply it by another matrix, which gives us a vector of 12 numbers, which can be interpreted as the relative likelihoods of our model's predictions for the next note. And at the start of training, the model might say, okay, F sharp is the most likely note to come next. But unless we're analyzing a data set with a lot of tritones, we probably know that that is not the correct answer, or at least a great answer. So instead what we do is we look at the real answer from the sequence that we're observing from the data set. And then we update the values of these matrices such that our model's answer for the output B goes up, and the model's answer for every other output goes down. So now we've arrived at essentially a neural Markov chain, but it still doesn't have any additional context. So we need one other piece of infrastructure, which is this notion of a summary vector. This is commonly associated with recurrent neural networks, where essentially now we have this vector which is this vector H, which is attempting to summarize all of the musical information that the model has encountered thus far in some sort of Euclidean continuous representation. And so we pass in, for every time we use the neural network, we pass in the immediately previous hidden vector, which summarizes all of the previous notes in theory, and the current note. So essentially we're kind of reparameterizing this language model into depending upon a summary vector and the immediately previous token, which is kind of roughly equivalent to, hopefully equivalent to all of the previous tokens. And if we do this, we can actually start to generate music that sounds at least somewhat cohesive. It's not great, but again, we're working with a very simple representation here. So this is trained on a data set of Bach fugues. It's just kind of wandering around. It's not super pleasant to listen to, but it's at least in a consistent scale, and seems to have some notion of direction. Cool. So that's kind of a very simple overview to neural network language modeling. Now in this next project I want to talk about, we essentially took this idea to the extreme, where we looked at a data set of very rich music data, so music from the early video game console, the Nintendo Entertainment System. These pieces of music are often referred to as chip tunes because they were sonified by the chip on the system. So we extracted pieces of music from games for this system, which ultimately look like this score, this piano roll that we have on the right. So a score for 4 individual instrument voices. And what we do to transform this into something amenable to language modeling is we simply flatten it into one big monotonic change list, which is essentially describes all of the points in time at which the piano roll changes. It's MIDI-like, if you're familiar with MIDI. And I forgot to mention this work with Henry, Ethan, Gary, and Julian. That's currently under review, so it's a little hush-hush, but all right. So essentially, if we train a very powerful neural network language model on this powerful representation of music, we can actually start to generate music that sounds a little bit more coherent. So here are some examples of some pieces of music that were written from scratch, or some chiptunes that were written from scratch by our model. Oops.
Do you have any examples of original chiptunes?
Not immediately available in the slides, sorry.
Is that what you mean by human?
Here's another one that was composed from scratch.
The guy stuck, that's only 3 parts, and there are 4 parts to a chiptune. Did it just decide to only have 3 parts going?
Yeah, I think in that particular one, it only decided to have 3 parts. So like sometimes it like leaves out the noise instrument, like in this one. This has the 3 voices, but not the noise instrument. But you can also do slightly more interesting things with this model in terms of composing alongside humans instead of just creating chip tunes in a vacuum. So here's an example of a rhythm that was specified by a human. And here's an example a tonal passage that was generated on top of that by our model. And since this is a distribution, we can run it again and get something completely different. And here's an example of a human composition over that same rhythm. This is actually from the data set.
Okay, so you did have an example.
Yeah, but I forgot, it was kind of in the context of this other thing. Yeah, so that's what the real ones sound like, or at least a single real one. So we can do some pretty powerful things with this relatively straightforward approach. But when I originally started talking about this probability distribution in music, I presented it as something that was operating over waveforms. And then I immediately started talking about instead scores. And so what I kind of did, it was a bit of a sleight of hand. What I did there is I kind of implicitly factorized this distribution over music into a distribution over scores, which were provided by our stochastic language model. You have a question?
Oh, before we move from scores,
Yeah.
Have you given any thought to using other, like a melodic contour, whether a pitch is going up or down or it's staying the same? And
Yeah, so I've been thinking a lot about like different ways of breaking down the process into more of like a factorized approach where, for example, you first compose the rhythm and then compose the contour and then fill in the notes, which I think would actually improve the model. But for this current work showing on chiptunes, we basically only went for the straight language modeling approach. But I think like that is certainly the direction going forward because that allows us to kind of interchangeably mix and match rhythm and contour and stuff like that.
Like the probability of a note staying the same is fairly important,
Right, yeah. So these are things that are kind of implicitly available in the language modeling form that we're working with, but yeah, might be a little bit less at the surface as they would be if it were broken down further. So I think that's the right way to go forward, actually. Yeah, so as I was saying, I kind of implicitly factorized this distribution over waveforms into 1 over scores times 1 of audio given a score. And in this case, I actually used a deterministic synthesizer, so calling this a distribution here is a little bit misleading, but in other contexts like piano, there might actually be a bunch of different things that could happen with the piano given a fixed score. So this kind of asks the question, can we model P music directly? Like, so we had the opportunity to model scores on our chiptune data set because we had access to those scores. But for most music data sets, or for most music in general, we don't have the symbolic representation. We only have the kind of acoustic artifact that we can listen to. So this was the idea. This question was the motivating question behind a recent work called WaveGAN, which I did with Julian and Miller. And the high-level overview of how WaveGAN works is that we have some Euclidean space referred to as a latent space. And in this case, for example, it's just 2 dimensions. In practice, it's usually much higher dimensional. But essentially, the point is that each of these dots in this space represent an individual piece of music or audio waveform, if we're not studying music. But the hope is that neighboring points in this space are semantically similar. So essentially, if 2 points are close together in the latent space, they should ultimately sound like very similar pieces of music or audio. So if we take one of these points, any of these will do. We have something called a latent code, which is a vector that basically is a compact representation of a piece of music. And we feed it into a neural network model called a generator, which will output a musical waveform. And so the hope here is that because this latent space is actually continuous, that we could actually build interfaces that allow people to navigate in this latent space by essentially moving around and trying to find, moving coarsely to find the types of things the kind of broad types of things they're looking for, and then fine-tuning with smaller movements to find the specific piece of music that they have in mind. So this would be a really powerful thing to have, but unfortunately, like, it's not entirely clear how we would actually train such a neural network to be able to do this. So the way we do this is with something called generative adversarial networks. And how these work is essentially, we start with some big bag of music, so a bunch of pieces of music that we're interested in, which are essentially kind of implicit samples. We're treating them as samples of some probability distribution of music that we're hoping to characterize. So we pick one of them at random, and similarly for the synthetic side, we pick a latent code at random. So pick some random vector associated with a piece of music, and send it through a generator, which will output some signal. Now at the start of training, it's very unlikely that it'll be anything musical. It'll probably just be noise. But how we can actually improve the generator over time is by using this other neural network called a discriminator, which is trying to determine if a given piece of music that is input to it is real from the data or fake from the generator. And by pitting these two neural networks against each other, by which I mean training the generator to fool the discriminator and training the discriminator to learn the differences between real and fake music, we can actually work towards a generator that produces plausible music. So here are some examples of a waveGAN that was trained on 4-second clips of jazz piano from Art Tatum's solo masterpieces. So here's some real, first let me play you some real clips. Oops. And the visualization you're seeing is just the results from a transcription algorithm on the audio. Those are some real examples.
Are the gaps because they're...
Because they're individual clips. Yeah, that was 3 clips just now. So here are some other clips. Here are some clips, some generated clips from a waveGAN, which is trained on the same material. So what this says to me is that the algorithm has done something interesting where it's kind of learned overall what the sound of the piano is and what it means to play individual notes on the piano in waveform space. And in my opinion, all this is very subjective. It's actually started to capture some gestures which are associated with Art Tatum's playstyle, such as very fast runs up and down the piano or slower blocked chord sections. But clearly we still have a long way to go to actually, capturing this distribution precisely. But what this technique is more useful for in the short term is actually generating sound effects. Now this could be really cool because musicians, music producers, film scores, sound designers spend a lot of the times basically scouring large libraries of sound examples, trying to find specific ones that fit for a particular part of the song or a scene. And so if we actually had a continuous space that allowed us to kind of interactively and in an exploratory way find sounds that we're looking for, it would be a much more productive way of searching. So here are some examples of some generated drum sound effects from waveGAN. Cool. So you get the idea. Plausibly drum sounds, still some artifacts here and there. But overall, certainly sounds that might be useful given some post-processing. Okay, so that's kind of an overview of my ideas about using machine learning to model music. And so now I want to talk a little bit about interactive systems I've built which take advantage of these systems. So, and one thing I want to emphasize here is that even these imperfect machine learning systems, like systems that have not completely captured the distribution that we're looking for, can still be combined with familiar musical interfaces to build useful things in the present day. So I want to first talk about this project called Neural Loops, which is a project I recently did in collaboration with my friend Vibert Theo. And the idea of Neural Loops is basically to merge 3 different generative models of music in an interesting way. And so we have this model Music VAE, which I did not have any part in developing. It was developed by some colleagues at Magenta. And essentially what Music VAE does is it produces a discrete score for 3 instrument voices, a melody instrument, a bass instrument, and a drum kit. And so we combine this with this model GANsynth, which I also worked on, which generates instrument timbres given a desired pitch. So essentially it's kind of a continuous representation of tonal instrument timbres. And we combine that with my WaveGAN model, which was trained on drum sound effects to provide timbres for the drum kit to use. And if we feed all of these outputs into a musical sequencer, we can get waveforms that we can listen to, which essentially this represents kind of a factorized approach at modeling a distribution of acoustic 4-bar loops. So I'll switch over to a live demo now.
Sorry, why is it called loops?
Because they're 4-bar musical phrases that are kind of designed to wrap around and be replayed ad nauseum. So here's an example loop that was composed from scratch by the system. So you hear it loop now. And so this is a very familiar kind of music sequencer. We can do things like increase the reverb or slow it down a little bit, or lower the volume ideally.
Have you tried making it traditional, like training it on Hendrix and Cream and?
Well, so we don't actually we haven't tried changing the model that's generating the scores. So I guess the answer is no. But what while this has kind of familiar musical controls, it also has these, for lack of a better phrase, intelligent controls, which allow us to do things like procedurally change the melody timbre, or change the bass timbre, or we can change the entire drum kit if we don't like the drum kit. I don't like that one. Let's try a different one. Or we can actually just change the entire track and generate something completely new, which, so that's what you get. Yeah. So I would say this is kind of more of a proof of concept than anything, but it does, I think, illustrate a kind of an idea that current musical sequencers essentially assume expertise on the part of the user, whereas this sequencer, you can sit down with it and even as a non-musician immediately create something with it just by pressing these controls, which allow you to switch out. Actually, you can also, I forgot to mention, you can switch out the score for each instrument as well. So just being able to kind of press a button and be able to swap out components kind of changes the role of the user in the system from someone who's manually entering things into someone who's kind of curating through reasonable examples, which I think is a common theme of some of these models, where it kind of transforms the user from an explicit role into more of a curative and exploratory role. Cool. Okay, so that was an example of a system which is designed to use these audio generative models that we came up with. But now I want to briefly revisit this idea of using language models in an interactive system. So I want to revisit this slide I showed at the beginning of this task of piano improvisation and the steps involved. And I mentioned at some point that we don't yet have anywhere close to the technology available to do this dotted line here. But what could we do instead? What I proposed in a recent project is basically to kind of relax these intermediate assumptions. So instead of requiring precise musical language, we instead are going to we're going to only ask for an approximate descriptor of a piece of music in someone's head, using these attributes of rhythm and contour, which I'll soon describe. And instead of requiring a precise series of actions, we're only going to require people to perform simple actions on these kind of user-friendly buttons, arcade buttons that we've built here. And the idea is that we can use a machine learning system to transform this kind of approximate specification of a piece of music into one that we can actually play out of the piano. So to briefly describe rhythm and contour and why I think it's possible that we could capture musical intuition using these simple attributes, I want to give an illustrative example of the melody Ode to Joy, which Miller actually hilariously previously tried to put into the system. So Ode to Joy, of course, goes da 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 da. And what we want to do is we want to represent that as the combination of its rhythm, so the precise specification of its rhythm, as well as instead of the individual pitches or even the relative pitches, we want to represent it as a contour. The idea of contour is essentially to condense the pitches, the precise pitches, into more of an overall shape that describe the pitches. So we, in this popular codification of this from psychoacoustic research in the mid-70s, we have these 4 symbols. Basically, an asterisk implies the start of a sequence, and after that, the note R implies that the previous note has been repeated. The note U implies that the previous note is higher than the note is higher than the previous, and the letter D implies that the note is lower than the previous. So we can essentially just describe Ode to Joy as like a shape that kind of roughly approximates its kind of overall melodic form. And there's a lot of research that implies that this is kind of how, especially non-musicians and adolescents, represent music in their heads in order to actually like identify pieces of music that they're listening to. But there's also kind of implicit evidence that these are reasonable approximations because they're often used for imitation. So for example, in things like Guitar Hero or air guitar specifically, the player is asked to kind of move up and down on imaginary fretboard in air guitar in lockstep with the contour of what the actual guitarist is playing. And they're also kind of imitating the rhythm that the guitarist is playing by, pluckings on imaginary strings in time with the guitarist. And so while these attributes have been used commonly for imitation, they have yet to really been explored for real-time generative purposes. So can we actually generate music using these same attributes? So that was the idea behind a recent project called Piano Genie, which is work I did with Ian, Sander, and Monica at Magenta. And so the basic idea, the kind of genesis of this idea was loosely the concept of inverting Guitar Hero. So building a system which allows you to generate music using a very simple controller. In this case, this kind of miniaturized piano consisting of only 8 buttons instead of 88 keys. And so the idea is that we would like to be able to convert in real time, translate a performance on these buttons to a corresponding an intuitively corresponding performance on the piano. So we have a demo that I'll give you a brief demo of it now, and you can try it out for yourself at this URL. Okay, so this is what the demo UI looks like. It's basically you have your 8 buttons at the bottom and a representation of the 88 keys of the piano at the top. Currently, I have essentially what's happening is that the buttons are sending a signal to the computer, which is running the Piano Genie software, which is sending MIDI messages, so control signals to the piano, which actually select the particular note on the piano that we're going to play. But so if I play it, hopefully this works. Let me turn the volume up a little bit. If I play a button on this controller, I get a single note. There's a little bit of delay because this is an old disc clavier. But similarly, if I press 2 buttons, I get 2 notes, or 4 buttons, I get a chord. But importantly, if I press higher buttons, I get higher notes, and similarly lower buttons to get lower notes. So I'll just give.
Are those just up-down keys, or do they also play notes?
What? Can you rephrase?
Are those contour keys, or are those note keys?
They're essentially like, so if you play a particular,
ones on the end is what I meant.
the colors don't really mean anything, unfortunately. They're essentially, yeah, like towards this end is like the high end of the piano, and towards this end is the low end of the piano.
I got that.
Okay.
It's just, if you hit any button, does it go over and over? Does it go up or down?
It depends on the button. So it's a learned mapping. So like if I press middle buttons, sometimes it'll kind of like wander around. If I press top buttons, it usually like moves up.
Okay.
So I'll just give like a brief improvisation now to kind of demonstrate the system. Thank you. Yeah, so if...
So when you do that,
Yeah.
you don't know exactly what's gonna come out, right?
Yeah, so I kind of have how I find myself experiencing it is as the piece progresses, I have kind of a rough idea of where I want it to go next. But when I press an individual button, yes, I don't know exactly what's going to happen. But it's surprisingly intuitive to be able to just kind of give yourself up to the system. And that's kind of why we called it Piano Genie, because it's like a an evil genie. It might grant your wish, but with like an evil twist or something. Yeah. Okay. But how do we get there? I showed a demo, but I didn't talk about how we actually built the system. So how we got there is that we started with a data set of piano training data consisting of hundreds of MIDI performances of skilled musicians. And this represents virtuosic classical piano repertoire across many different eras. So essentially what we're hoping to learn is kind of this distribution that characterizes a homogeneous sampling of classical piano music. And how we're actually going to learn to translate between the buttons and the piano is by adopting what is commonly referred to in machine learning as an auto-encoding approach. So essentially what this means is that we start with some representation of the piano sequence over 88 keys, and we pass this through a neural network called an encoder, whose job is to output an equal length sequence over instead 8 keys. And then similarly, we pass the 8-key sequence into a decoder, whose job is to reconstruct the original piano music that actually went into the encoder. So by training this thing end to end to kind of minimize the decoder's error with respect to the input, we're essentially forcing the encoder to learn to represent music in a much more compact space consisting of only 8 buttons. And then similarly, the decoder is having to learn to decode from that space back to the original space. And our intended interaction is that we're going to essentially replace the encoder with a person performing on the buttons. So every time the the user presses a button, it essentially queries the neural network for a reasonable note, and then outputs that note. And then the next time a user presses the button, it gives us another note, but that note is not only conditioned on the button the user pressed, but also what the model has output in the past, because this is actually a neural network language model, as I previously described. So essentially, like over the course of time, we can actually build things that make sense with themselves and what has happened in the past. So having things that have like consistent key.
Perhaps you're going to say this, but what makes it think of those? What makes it not just permute randomly those 8 into some other?
Yeah. So
how does contour go to contour?
Great question. So yeah, next slide. Yeah, so essentially, you're correct. Out of the box, the neural network would have no idea what these 8 buttons mean, and no idea that we have this hope of them corresponding to this idea of contour. So what we actually had to do is come up with a way of characterizing the relationship between the contour of the input piano sequence and the button sequence that the encoder produced, such that we could actually minimize the error between the two contour representations. So essentially, like if we multiply, a little bit verbose, but if we multiply like the finite differences in the piano sequence by, the intervals in the piano sequence by the intervals in the button sequence, whenever their signs disagree, that's essentially what we're trying to minimize, if that makes any sense. So this is how we were actually able to regularize the model such that it produced button sequences that had the same shape as the input piano sequence, and similarly the decoder learned the same semantics. So now that I've kind of described a little bit about how this worked, I want to talk about a recent application where this system was deployed in a performance by the band The Flaming Lips, which was pretty cool. I want to show a brief video of the keyboardist from the band encountering the system for the first time and playing with it. And so what you'll notice is actually playing on a plate of fruits instead of these 8 buttons that I have. And this actually came out of necessity because they didn't have the buttons available, and this was the easiest 8-button thing they could construct.
What are you using to know which fruit he's hitting?
There's little electrodes in each of them that just send like a discrete signal to the computer. But what I think is really cool about this is like, this is the first time he ever used this and was kind of immediately able to understand what was going on and use it in sort of a very intuitive way. But also it's kind of like challenging him in some ways, like creating things that surprise him that he wouldn't have created, and so in that sense it's somewhat interesting. It's the flaming lips.
That's a good point, yeah.
So this isn't the entire 1,000-something sequence, bunch of classical music that's in there, there are smaller tracks.
It is actually the same.
Really?
It's just the timbre that they're using that makes it seem different.
Yeah.
I just like that because it's a lot better than the demo I just showed you. Even though it's the same model, I don't know, it just came out very well, or very nicely. So while this, fruit plate came out of necessity, it was just like the easiest way for them to whip up a specific controller for this. It actually ended up kind of spawning this whole idea of a visual metaphor for these buttons, of using fruit. So where like a larger fruit like a watermelon corresponds to a lower button, and a smaller fruit like a grape is a higher button. So the singer from the band actually designed these like balloons, which were eventually used in the course of a performance to allow the audience to interact with Piano Genie in the same way that people were interacting with it before I started this talk. So here's a brief video of the performance. So essentially how it worked is that the keyboardist from the band came out on stage and kind of gave like a demonstration using the plate of fruit of what the audience was about to do to kind of let the metaphor develop. So they also linked it to this timbre of actually like saying the individual fruit identities. So eventually what happened is that the band continued playing in the background. So we actually had to extend the model to be able to integrate with the context of what the band was playing. But then they threw out these balloons, which allowed the audience members to, every time they hit them, it would ask Piano Genie for a note, and then play that note over the speakers. There's a whole video you can watch at this link below. But while this is kind of an idea, it's something that I never had intended for the system. I thought it was really cool that it basically shows that the system could be used to enable a new musical interaction, as the title of my dissertation, but also to kind of just add value to like allow the audience to feel like they're part of the performance rather than just kind of an observer. So I want to close now with this quote by musician Nick Cave, which I thought, from a recent essay he wrote about artificial intelligence and music, and I thought it was really cool, where he said that AI would have the capacity to write a good song, but not a great one. And to summarize what he meant by this in the course of the article, he essentially was saying that one of the reasons that we find music so captivating is that when we see a performer doing something that we don't think we could ever do, it kind of, in some way, represents them like moving beyond their limitations and is kind of just like awe-inspiring to watch. But an AI system, while it has its own limitations, doesn't necessarily have the same limitations as a human would. So ultimately, just the fact that it doesn't have these same barriers means that anything an algorithm might generate, even if it's as good as something a human could generate, might ultimately not be as interesting to people. But I want to kind of co-opt this quote for my own purposes and say that AI alone would have the capacity to write a good song, but not a great one. So basically, like if we build systems which allow people to use these tools to create new and interesting things, we could actually continue to build systems which inspire people. So with that, I will say thanks. Take it easy.
Think you could get latent spaces down to such a small dimensionality that you could just sort of get, sort of waltz around a bunch of possible musical outputs with a joystick, or do you think that?
It's a good
really,
question.
Right.
I mean, certainly there's some transform that you could do to compress a high dimensional latent space into one that would, be approximately navigable. But it would certainly like kind of reduce the overall richness, I guess. But I think for things like sound effects, it's a little bit more likely that we could actually, you know, swim around in some 2D or 3D space that allows us to find particular sound effects that we're interested in. But for music, I'm not so sure.
Right, so I guess really what I want you to dilate on the question of what are you going to do when latent space really has to be 10 or 100 dimensional? Like what general approaches do you see to organizing that?
Yeah, so there's some work that exists which essentially tries to like take a couple of dimensions of the latent space and call them like the important dimensions, and say that okay, those particular dimensions should have very high degrees of mutual information with the output music from those dimensions. So essentially, like if you vary in those dimensions, it should change the music a lot. But if you vary the other dimensions, it's sort of this concept of like incompressible noise. Like, you know, to make it concrete, like imagine one of these things trained on snare drums. Now, these two dimensions that I'm describing might kind of swim around strong attributes with snare drums, like the punchiness or the amount of reverb or something. But these other like incompressible attributes might do things just like change its phase or like change its offset slightly, like less semantically meaningful things. So that could potentially give us, this is an algorithm called InfoGAN, if anyone is familiar with this literature. So I think these kinds of things could actually allow us to potentially build semantically meaningful, you know, low dimensional latent spaces that we could navigate in. But we could also do post hoc things like finding interesting directions in high dimensional latent spaces and mapping those onto, you know, a joystick or whatever. Thanks, Bob.
So when you train the Genie, the corpus is very eclectic. I was wondering if you went the other way and restricted the corpus, say, to a specific performer or composer, would you experience things that are more like that composer or that performer?
Yeah, so we've tried some simple experiments to train it on a particular performer. Like when I was doing, like I trained it on a data set of jazz piano improvisation transcriptions. And because there was this additional confounding factor that they weren't MIDI performances but were transcriptions from an algorithm, ultimately the model wasn't as compelling as, qualitatively speaking, as the model that was trained on the classical piano music. But I do think, yeah, if we had a corpus of data, a large enough one of a particular performer or composer, it could, hopefully it would capture some stylistic information about that domain.
Or you could do it like DJ does and just have make it conditional on whoever's playing,
Yeah.
whoever's composing.
Yeah, that would hopefully work, yeah, I agree.
So if you keep pressing the same button, right?
Mm-hmm.
Every time generate slightly different variation. Right?
Yeah.
That's part of the idea.
Yeah.
So that's where the variation comes in.
Mm-hmm.
Now what happens if you start performing and now you're happy with the melody, you want it to be a theme,
Mm-hmm.
then you want to have a chorus, then you want to have
Right.
chorus again,
Yeah.
you want to have chorus, you want to have development. You will play the same buttons, you will never get the same.
This is true. So yeah, I would say that this is definitely a limitation of the model. So one thing that we originally thought of with the system is that I don't know how many slides back it is, but like going back to this this encoder decoder. So one of the originally when we were building the system, what we did is we had the encoder transform the piano music, some length of piano music into not just an equal length sequence of buttons, but also some continuous vector, which attempted to capture all of the information that wasn't encoded in the buttons, essentially, which would potentially allow the decoder to be conditioned upon this other summary vector. So you could potentially like pass in a piece of music that you care about through the encoder and come up with its summary vector, and then kind of like intelligently remix it using the buttons, given that fixed summary vector. But we kind of, and so this would allow you to, you know, if you built a sophisticated enough interface, would allow you to actually repeat certain sequences in a controllable way.
But by construction, you'll have variations every time, unless
Yeah, but in this form, yes, by construction.
unless you sort of have some sort of a almost hard encoded memory.
Yeah, that you could also do it post hoc with some sort of hard memory
So
source.
the question is there a middle ground?
Yeah, so we actually tried, one thing that I tried was using different types of sampling methods, like sampling methods that would actually keep track of a post hoc history of things that you'd done in the past, and if it identified like a sub string of buttons that was the same as something you'd played before, it would try to output the same sequence. But ultimately, like I had trouble tuning that model to actually be intuitive. Like overall, it felt more rigid than the current form. So, you know, I mean, we made a lot of simplifying assumptions just to build something that kind of was fun to play with. But yeah, I agree that there's still a lot of things you could do with it to improve the controllability.
No, it's mostly the compositional design.
Yeah, the compositional, like the high level form controllability.
Storytelling.
Right, yeah. Yes, Ryan.
Do you see the potential of this maybe being like a training device? Like maybe people master this, like, well, I really want to learn the piano now. And
Yeah, I definitely think it could help. Like you can kind of imagine an interface like a digital keyboard which has the buttons on it and also the 88 key keyboard. And when you press the buttons, you can kind of see, you know, through like light up keys or something, what's happening on the keyboard. And then if you found a passage that you liked, you could, you know, try to play it and learn how to play it. And I think that could be really compelling because, you know, while traditional musical instruction kind of emphasizes like rote skill perfection, like, you know, going through scales really quickly and going through cadences and things like that, this would actually encourage more early on in piano pedagogy, like exploratory improvisation. And I think that actually could potentially like decrease the renunciation rate associated with, you know, people studying piano, which I think currently is quite high. Like people might try to start studying piano and then drop it very quickly because it takes years and years to be able to get to the point where you can create something that you want to create.
But couldn't it end up like the way elementary school teachers tolerate misspellings and then kids never learn to spell?
Potentially, yeah. But I mean, it's a good point. My kind of defense against that is like, okay, so ultimately,
Says your defense.
yeah. As soon as I said that word, I was like, oh, that's good. Ultimately, someone who does take the time to master piano improvisation is going to have the ability to express their musical intuition in more powerful ways than someone who uses like an approximate method. Because like it actually gives you the freedom to do exactly what you want to do. So yes, it could have this effect where people kind of go halfway and can only play the piano partially. But I think overall it might incentivize people to learn how to play the full instrument such that they could actually you know, remove the limitation of having a model approximate good music for them.
Yeah, it just seems like you could be done, right? I mean, this could be, there could be now bands like, you know, Fish Prime or something where they never learn to play their instruments like the punk bands of the 80s and
Yeah.
just do this.
Yeah, but again, I really think that overall, it's still going to incentivize people to learn the more precise control mechanism because like eventually they're going to hit a wall of things they can do with these approximate methods and want to have full control.
I mean, I can rephrase the question otherwise maybe. I mean, you go from low dimension to high dimension, right?
Sure, yeah.
Saying that somebody doesn't know. But what, I mean, can a professional musician start with this high dimension and have the system basically accompany him to the level of another musician? So it doesn't have to be, I mean, could you extend this approach that way? Because you went pretty much from low to high. You can do high, low, high.
Yeah, so like, again, one kind of concrete example I might think of in terms of this system is like, okay, you're a professional keyboardist and you have some solo in the you know, a verse of a song that you play frequently. And you know, once you play that song 100 or 1,000 times, you kind of are in some sense like locked into that exact thing that you play, like maybe with some minor deviations here and there. But maybe what you could do with this system is play that solo through the encoder, and the system, a version of the system which has like some sort of summary vector that is outside of the buttons, like that I described in a previous question. So there's some continuous representation of what you just played. And then essentially what you could do is use this system to like, you know, play the same contour that you would usually play for that solo, but see if the system would come up with, you know, kind of surprising and nuanced deviations that you would, at this point and how many times you played it, kind of ignored.
Did you try sort of a dialogue system?
No.
Like, you know, having this as your accompaniment, so it doesn't imitate
Yeah.
creates.
I mean, so
Like chatbot.
yeah, like the version of this model we built that was conditioned on chord progression for the concert that I just showed could kind of be thought of in that way, where it's like, you know, it can be just another instrument that is playing alongside a fixed chord progression that the rest of the musicians in your ensemble are playing. So in that sense, we kind of investigated it, but not really like formally or anything. But I do think that was kind of the original intention for the idea. Is like, okay, if we're at a show and this model is tracking the chord progressions that the band is playing, could we just give these buttons to like someone in the audience and have them do something that, like, there's basically no potential for it to be musically disastrous, but something interesting could still happen where the audience member feels like they're involved now. You've been waiting to ask a question for a while.
Yeah. I mean, I see a value in this type of interface. It's like a drum machine or Ableton Live where you get this immediate gratification just putting things together. And
Right.
I mean, like a drum machine, I think it could lead to its own virtuosic experience that's quite apart from the piano.
Yeah. I hope that would be awesome.
Now, one thing I was wondering if you were thinking of having the thing trained by the person performing the buttons, like by selecting the things which they tend to go for.
Yeah, in theory, you could like fine tune the model based on a particular performer. I think that would be a really cool way to you know, cater this model to a particular person. But it's that's one of those things that's really challenging with these deep learning systems right now, is that intuitively, or not intuitively, actually pretty non-intuitively, they don't actually. If you're showing them like a small amount of data and attempting to retrain them on that, it's not going to work very well. Like ultimately, that's still kind of a restriction and something that would be hard to overcome. But if you had someone like use this model for weeks and like constantly be playing on it, then maybe you could kind of fine tune it to their characteristics. But I think also that could potentially have unintended side effects where it ends up becoming too catered to you and no longer like surprises or challenges you. So like, it's not at that point, if you just have this model that does exactly what you would have done in every situation, like, is that what we want? I'm not sure. But yeah, I think.
Well, only if it could be trained on you trying to break it out of that.
Right. Yeah. I think there's probably some middle ground that would be better than either endpoint.
Mm-hmm.
Yeah.
So one thing you might have tried, what would happen if you got rid of the physical buttons and simply put someone at a piano, a real pianist, and asked them to play some Chopin?
Yeah.
Put them through the
Encoder.
encoder and then the decoder, and
Yeah.
then you get re-decoded Chopin.
Yeah.
And of course you would have done that to try to figure out if the thing was working.
Yes.
What happened, or do you even have any examples of that? Because that would be wonderful to listen to.
Do I have examples of that offhand? Unfortunately not. But in my experience, okay, so the model that we had, when I've described this like idea of having the encoder output a summary vector several times. Is that something that makes sense to you? Okay, yeah. So when we tried that originally, like if we had the model output, like for example, a four-dimensional continuous summary vector of like a 128 note sequence of piano, we actually saw that the decoder, alongside using both the vector and the buttons, actually approached like 100% accuracy for decoding. So it was actually able to compress, you know, kind of stylistic and information into this continuous vector, and then kind of the more nuanced individual note information into the buttons. But the version that doesn't have the summary vector, of course, does not get anywhere close to perfect reconstruction.
Right, that's what would be fun to listen to.
Yeah, I agree. And so, yeah, I think informally, like from just observing this, yeah, it never sounded like Chopin, but it would have the same contour, and it sounded okay overall. I actually, okay, so the more nuanced, a nuanced part of my answer to that question is that when we listen to these things during training, we're actually doing what's called teacher forcing on the decoder, where instead of giving the model its own output for input at the next time step, we actually give it the real note from the data set. So essentially, like, it's actually only having to predict the next note in the sequence at every point in time. And so actually, like for classical piano music, it is actually able to do that pretty well if it's forced, if you provide the sequence shifted by one time step as its input. But yeah, actually, I'm not actually sure if I've ever listened to a real contour and rhythm input into this model without teacher forcing, actually just sampling it. So.
You answered what would have been my next question.
Right.
How on earth you figured out whether the decoder was working or not, but I guess that was the teacher forcing step.
Yeah, well that, but also like the kind of the notion that I presented earlier on about the relative likelihoods between different models. So like basically like looking at how what the probability of like how closely the probabilities of the decoder aligned with the actual ground truth
Okay,
sequence.
so not looking at what the decoder put out, but looking at whether the decoder thinks it was probable that the melody that you actually, or the piece that you actually put in, could have happened.
Exactly, yeah. Just like trying to maximize the likelihood of the particular piece. Yeah. So,
I have a question, not any specific model, but you tried several of them.
yeah.
And so how do you know which one is better?
Yeah, so I kind of took a lot of this information.
What's the musical quality of the generated sample? How do you measure this?
Okay.
Is this
I don't actually have
satisfaction
slides
or
of this.
statistics of the output? Or
Yeah, so essentially what we did was look at like quantitative measures in terms of validating hyperparameters, like comparing between different models. We basically just looked at the metric I had mentioned early on about asking how likely Twinkle Twinkle Little Star is under the two distributions. So just comparing, the perplexity or the negative log likelihoods of the model. And then once we found the model by that measure, which performed well, we did run a small user study, basically comparing three different mappings from 8 buttons to the full piano. The simplest of which was like mapping the 8 buttons to a deterministic major scale. And another one was mapping the 8, every time the user pressed a button, it would actually just evaluate a language model of music that wasn't trained on the buttons. So it wasn't an autoencoder, it was just like a language model of music. So the theory was in that model you had control over the rhythm of your performance, but not the contour. And then we compared it with our like contour regularized model. And asked users various questions about the experience, and it was favorable for Piano Genie, but it was it wasn't a very in-depth user study.
so what would be the next goal musically?
Yeah, I mean I think the goal is to continue to build interface, like figure out some way to. Honestly, the question you asked is in my mind kind of the most immediate next goal of figuring out how you get the thing to repeat musical phrases over time. I think shallow answers to that might be using more sophisticated language models, which might be able to memorize past sequences and improve them accordingly. But also, those models wouldn't be capable of running in real time on my laptop, so it would be a bit of a step back in that regard. So if there's some other way to control repetition in musical form at a higher level, that I would see that as like the most pressing next step. Jen?
Well, Ableton has this thing where like you push it after you play something on MIDI, you push it and play the last like thing you played, as long as you move it back to the first note you played.
Mm-hmm.
So you do like 4 notes from that.
Oh, cool, yeah.
That. But I guess you need like some kind of interface to be able to repeat it. But like the way it works right now, it's like it kind of always does the same thing. I mean, like it's always changing, playing a different phrase, but like there's no like parameters to say like do this more, like play around here more, and do this more. Like, is there any way to add things like that to it?
Pedals.
What's that?
Pedals.
Yeah, potentially. I mean, so one thing that I would like to relax is this idea that each button only plays a single note. So this is actually something I designed, and I think was a little bit biased towards my experience as a pianist, that I wanted to maintain these semantics of every time I pressed a particular number of buttons, getting the same number of keys out on the piano. But when I give this to people who genuinely have never played a piano, a lot of the people are a little bit disappointed that like a nice run doesn't come out when they press a single button or things like that. So I think I'm not even actually sure if I'm answering your question really, but like basically relaxing the association between the control interface and the piano and catering it more to particular people might help. Did that answer your question at all? I'm sorry.
Yeah, I guess I was thinking like, so for some people, if they like pushed it, it would be like if the runs it would play
Yeah.
more, or like
Right.
if somebody wanted it to react less to them, something like that.
Yeah. I think there's some way of providing some sort of continuum that a user could specify where they're like, okay, I want more of this or less of this. But currently in the system, like the way we set it up is that the interface is really heavily baked into the training algorithm itself. And so it's not easy in its current form to adjust things like that, but I think we could alter the algorithm to hopefully achieve things like that. Yeah, I think like user tailoring, in addition to this music idea of repetition and musical form, are kind of the two most immediate drawbacks. I was
just going to, I was sort of raising my hand at the same time as Jennifer. It seems like there's this possibility for a button, as said, but I liked what happened. You know, it's sort of like a,
right.
I want to explore this further. So you hear something and then you can immediately react it by hitting another button. You know, just you could have one button that was separate, and then the algorithm might take just in that binary information that, you know, they liked it or not.
Yeah.
And then further explore whatever gesture or musical sequence was presented at that time.
Yeah, I definitely agree.
That's what I meant by pedals.
Yes or no?
Say, yeah, more of that.
Yeah, so I mean, I think
just more of that in the same, like in a repetitive way, but rather explore that gesture more in depth. You know,
right.
Like use that as thematic material that would recur in some permutation, or you know.
Yeah, I agree. So like, you know, one kind of, again, this is kind of just like an inherent limitation of these kinds of systems, is that they're very hard to retrain on like small amounts of data. So anything a user could provide in an intuitive amount of time is not like something that the model could currently be effectively trained on. But that's like a really defeatist attitude. So I think there are ways that we could, you know, attempt to do these types of, you know, fine-grained feedback and make kind of dramatic changes to the model's parameters, but I've yet to explore that, and I think it would present a lot of challenges, but could be really interesting and useful.
Well, you wouldn't want to have to retrain the network in real time, but one thing that you could do, perhaps if you went ahead and kept the extra dimensionality in the latent space, is you could have the thing flitting around at random in the latent space. And
yeah, that's true.
When you liked it, stick to one area.
Right, that makes sense too. Yeah, I guess it's also a question of whether or not you want it to be like adaptive within a play session, or like adaptive across many play sessions, like a long period of time.
Right.
It's unclear, like.
Yeah, I guess I'm thinking within a single session, that would be a thing that maybe you could try.
Yeah, so really the biggest takeaway I've had of this experience of building this thing so far is that literally everyone wants something different, and it's very challenging. And you know, I'm not saying this as like we shouldn't, like that's and you know, people are always going to want to use things in different ways. So we have to build systems that actually allow us to adapt to individual preferences. But it just becomes very challenging very quickly. And currently, yeah, it's still not something we've looked at, but I really want to and really intend to in the long run.
George Lewis used to have a boredom signal.
Yeah.
He would look,
right.
He would watch out for boredom, and if boredom happened, he just go change something.
Yeah, I like that. How was boredom expressed in his system?
Well, he was just looking for simple statistics, and if things weren't changing, then he would just change something.
I see. Right. Okay, just like an indicator of whether or not it had gotten stuck or something.
Yeah, right. Exactly.
Yeah, that could.
That was
cool.
like 1970s, so.
Right, but yeah.
More like a guiding beacon than a specific idea for a technique.
Right. Yeah, I guess so. I do like that. At some point, I should probably like, if people are free to leave if you want, but we can also keep asking questions. Like if you feel like you're stuck, feel free to get some food or go out or whatever.
Looking at wave-GAN and spec-GAN and the sort of idea of browsing through kick drums or something
Yeah.
that, it immediately makes me think, just all the musicians who are surfing through presets on keyboards, and I was wondering if you had any ideas towards looking at synthesis parameters as a type of thing you could explore, especially since there are so many presets out there. You actually have a body of information you could train on.
Yeah, so it's hard for me to jump around slides. Okay, so I'll just explain it. Yeah, so I really think there's this idea that was proposed by Hugo Scardo and Rebecca Febrink of this idea of like grab and play mappings, which I think essentially what they meant by that is like I should be able to pick up any arbitrary controller, do some stuff with it, and like automatically map it to any other arbitrary controllable interface, like the parameters on the synthesizer or something like that. I think this is a potentially a really powerful idea of which, you know, Piano Genie is one very specific instantiation of this idea. But if we could actually build more general systems that through some means allowed us to map arbitrary, you know, spaces or control interfaces directly to our other like semantically meaningful ways of navigating other parameter spaces, that would be really powerful. And something I definitely want to work towards, yeah. I hadn't actually thought of specifically looking at synthesis parameters though, and I think that's a really cool idea. I wonder, like, because, you know, different synthesizers have very different sets of parameters.
I just think of the hundreds of DS7.
Like DS7, yeah. That could be really cool, yeah. That would be a really cool project to generate DX7 patches, yeah.
The tough thing about that is, depending on, lots of the times you can change a parameter, nothing happens to the sound.
Right.
So it's not, there's no reasonable distance measure between one parameter, you know, one collection of parameters and another.
Right, but you can think of a collection of patches that people have configured as, you know, at least
Single points.
points that are meaningful, and then maybe you could connect the dots, potentially.
I doubt that'll work.
Yeah, maybe.
So it kind of leads to the question of, you know, in your latent space representation, I mean, is it compositionality in the sense that this plus this is like this plus this, or you know?
Mm-hmm. Yeah.
I mean, does it actually have a structure?
Yeah, so we explored this a little bit in terms of drum sound effects and other domains, like we trained it on bird sounds, and did find that it wasn't like quite as intuitive as these kind of these algebraic properties associated with image scan latent spaces, where, for example, you can like put glasses on someone by adding a glasses vector. But I think part of that is the fact that we actually have to listen to these things, as opposed to images where we can look at 5 images in a line and see if they're semantically interpolated. We have to actually listen in real time to 5 audio signals and think about whether different points in time in those audio signals are related to one another. So like visually there's some similarity between the spectrograms, for example, but it was a little bit challenging to hear acoustically in my limited experience actually investigating that particular question.
So, back in the day, I used to write these humorous abstracts as invitations to my parties.
Okay.
One was...
I love this story already.
One was Jimi Hendrix meets the giant screaming Buddha, recreating the 60s through backpropagation in time. And the proposal was, they all had like actual ideas in them. And in this case, the proposal was to train a network to map from scores to the way Jimi Hendrix played it, like
Reinvent the style. Or his
yeah,
style,
so the way he played the Star Spangled Banner, for example. And
right.
so the punchline was, now we could see how he would do Don't Worry, Be Happy. So
right. What do I think?
So style transfer seems like something that's now possible in this domain. And is there any work on that, and who would, you know, like Deep J was a kind of a version in the sense of just generating from a combination of different authors, but in this case it would be like giving it the score and the style. And
yeah, so I think of that again as like another factorization of, you know, the score into the probability of the binary score times the probability of like the expressive attributes given that score, like rubato or dynamics or things like that. And there's been a good amount of work on that. Like essentially, I think that the kind of the field, name for the field is like expressive performance, or like learning to perform, essentially. Although it's only very recently adopted machine learning approaches. So actually, we had attributes of this in a paper, in the earlier paper that I did with Henry on the chiptune stuff, where we were essentially trying to invent the extra information on the synthesizer, like the dynamics, by which I mean the volume, and and like there's also like timbral things you can change in the synthesizer that will make it sound a little bit different. So we basically tried to reinvent those given the score, and had a reasonable amount of success doing so. Now I'm actually starting to see a lot of work on this problem. Like there's a piece of work at this year's ICML that estimates piano performance interpretations for specific performers given a fixed score, and I think that's, yeah, their results were pretty cool, and so there's work on this that is happening. Yeah. I think it's challenging, like if you wanted to specifically do like the Jimi Hendrix thing, like there's a lot more there than just the kind of symbolic representation of what he was playing. Like a lot of his performance was this feedback interaction between his guitar and the amplifier, which is inherently like a very acoustic domain thing. And so it would intuitively, to me, it would have to be some sort of acoustic domain method to actually accomplish something like that. And there's a lot of acoustic domain methods that attempts to do things like timbre transfer, like transferring from some piano audio waveform into like the same waveform on a harpsichord or something like that. And their results are pretty good, but the ultimate limitation of those systems is that currently they don't adjust the timing in any way, because they all use conv nets and just assume that the timing between the input and the output is aligned. So that's inherently not going to work for, you know, a very large portion of the characteristics associated with particular performers in terms of their timing or rubato. And so I think we still have a lot of work to do to make it like a dynamic time warping kind of thing.
But your representation with time intervals, you know, on, time interval off, could cover some of that.
Yeah, potentially. Yeah, this is true. But again, that's symbolic again. So we're now throwing away like all the other attributes. Or, I mean, you could possibly combine
That's
them.
been one attribute.
Sure. Fair enough. I'm getting a thumbs up. Okay, cool.
Why didn't the piano genie play different notes when you played chords?
Why didn't it play different notes?
Yeah, it seemed to stay on the same.
That's a good question. I think it does different things depending on what you do. Like, it will like move up. But yeah, you're right. If I do play like a block chord, oh no, it's moving. It kind of has gotten stuck though in like inversions of the same chord. Yeah, it's sampling, but, you know, it's, yeah, yes. It tries.
I have one question. In the neural loops thing,
Yeah.
it has like 3 like instruments.
Uh-huh.
Do they know what's going on with?
No, so that was a big, okay, so the scores know what's going on between them. So the timbres have no idea what's going on, but when we generate a score, it's actually like a score that's supposed to be, the 3 instrument voices are supposed to be related. We do make an independence assumption between the scores and the timbres. So like we make the assumption that any given timbre will work for any given score, which is probably not true in terms of human composed 4-bar loops. But that's just, you know, a nice assumption that we can use to build this decomposed kind of interface.
We just don't want to start another bench. Yeah, right. So many.
Yeah, it's true, actually. We can go on for days, have to stop somewhere. All right, I think it's time for the committee to
Convene.
deliberate. Yes, that's the word.
Should I leave as well?
So everyone
Yeah.
should leave.
Yeah.
Except us five, right?
All right, bye people on stream.
Oh, yeah.